Right, okay, matrices continued. We're going to do the inverse of a 2 by 2 matrix to start with because it's much easier. We touched upon it in the Zoom lesson yesterday, but let's just see exactly what I mean by that. So do put a title, inverse of 2 by 2 matrices. We'll just recap what an inverse is. So if I have, say, any number, let's say 9, the inverse really is whatever I need to times that number by to give an answer of 1, okay? And the inverse in this case is obviously 1 over 9, and we can also rewrite that. So inverse of 9 is equal to 9 to the power of minus 1. That's just a different way of writing the inverse of a number. And it works exactly the same way in matrices. So if we call the general matrix A, B, C, D, 2 by 2 matrix, then m to the minus 1 would be the inverse. Okay, so m to the minus, exactly the same notation. And also, like up here, if I did 9 multiplied by 9 to the minus 1, I get 1, and it also it's the same as the other way round. Doesn't matter about the order. I get the same in matrices. So if I do m multiplied by m to the minus 1, I don't get 1, I get the matrix equivalent of 1, which is the identity matrix. And likewise, if I did it the other way around, I would get the identity matrix in that way, okay? Right, now I'm going to take you back to the question we looked at in the Zoom lesson. So I think I used this matrix, so 2, 4, minus 1, 3, and the question was, okay, well, what is the matrix I need to multiply that by to give me the identity matrix, which is 1, 0, 0, 1, and that was the question. And effectively, we're trying to work out the inverse of 2, 4 minus, if I say A is equal to 2, 4, another way of posing this question is to find the inverse of A, which is this matrix here, okay? So what would have to go in there in order for us to give us the identity matrix as an output? I could have done it the other way around. I could have put the inverse first and it would have been the same. Now I'm going to do, we don't know what it is, so let's just call it 4 unknowns, x, y, z, and a. Okay, now I can multiply those two matrices together from what we've done last lesson. So the top term is 2 times x plus 4 times z. And the top right term is going to be 2y plus 4a. Bottom left, minus x plus 3z. And then bottom right, minus y plus 3a. That's if I multiply the left side together, and that must equal the right side. That hasn't changed. 1, 0, 0, 1. Now at this point, if I wanted to, I could set up a pair of simultaneous equations. I can compare elements. So 2x plus 4z must equal 1. I compare that element to that element. And I can do that for all 4 elements. So underneath I can minus x 0. I'm going to keep those separate to the other two, which you'll see why, because they're two different unknowns. So that top right equals 0, and then the bottom right must equal 1. Okay, so I've got 2 pairs of simultaneous equations here, which I can then solve to work out what x, y, z, and a would be. So if we look at the left-hand side, I'm going to use elimination. I'll times that one by 2 to get the x's the same. 2x. The other one, multiply by 2. And then if I add the 2 together, I get 10z equals 1. So z is a 10th. You can trust me on this one, but if I just substitute it back in, I get x being 3/10. Okay. Then on the right hand side, I'm going to do exactly the same. Times that one by 2. Minus 2y plus 6x. 2. Add the two equations, so 10a to a equals 2/10, and y will equal negative 4/10 there. So I can now put that back into my matrix here. So it was 2, 4, minus 3, 2, 4, minus 1, 3, and I need to, I would need to multiply that by 3/10. Z was 1/10. y there minus 4/10 and 2/10 there. And that would equal the identity matrix. And the inverse, if that's A, I have worked out the inverse. And that is one legitimate way you could go through that process every time to work out a 2x2 matrix, and that would be absolutely fine. But you'll be pleased to know there is a quicker way. There is a quicker way, and some of you may have intuitively spotted what could be done here. Now, if I was to multiply that matrix by this value, so if I switch the leading diagonal, and you might have seen there's a link there. If I switch, so these two, I switch 3, 2, and then I switch the signs of the other two. And if I multiply all of that together, you will find that I get 10, 0, 0, 10. Okay, that is similar to 1, 0, 0, 1, but it's a factor of 10 out. So on the left hand side, I would then need to put 1 over 10. I'd need to times it by a tenth, and then that would eliminate this issue here. Okay. So where does the tenth come from? Where does this matrix come from? And you'll find, so if I find the determinant of this matrix, remember that straight brackets there, it's 3 times 2, so 2 times 3 minus 4 times minus 1. And that does equal a 10, which does, and you can start to see why you are just doing stuff with the diagonals there, so it's not completely weird that that happens. And it is 1 over the determinant that scales it back down to 1. You'll see later on in the future chapters that the determinant tells you the scale factor of enlargements, which is again another really useful property of it. But in this case, we need to divide by that to bring it back down to an order of 1 and get us to the identity matrix. So, in general, we can say if matrix A is equal to A, B, C, D, then the inverse of A is 1 over the determinant of the matrix A, and then you switch the leading diagonal, so DA, and you switch the signs of that secondary diagonal, and that is the general point. You need to learn that. You will also find your calculator can do it, which is really useful. So if we get the calculator up. If you go into matrix mode again, and that A 2 by 2, and the matrix was 2, 4, negative 1, 3, 3. Okay, if I clear that, option map A to the power of minus 1, it will give me, yeah, it does give it to as a fraction 3/10, and so on. So that's exactly right. So you can get it on the calculator, which is really nice. Again, with algebra, you will need to know how to do it longhand as well. Now note, there are some, if matrix A is singular or det A, in other words, det A is equal to 0, there will be no inverse because you can't obviously divide by 0. So that is something to note. If you work out the determinant and it's 0, then you won't be able to find the inverse of that matrix. Okay. There is also another special feature that's useful. It's mentioned a little in the textbook. I'm just going to tell you the fact though. If you have two matrices A and B, the inverse of A, if you multiply A and B together and work at the inverse, that's the same as doing the inverse of B multiplied by the inverse of A, and the order is really important. Okay, so you must get it's definitely B inverse A inverse rather than the other way around. So the order is important there, but that's another useful feature of matrices. Okay, we're going to do a couple of examples and then I'll set you on your way. So EG1, if you say matrix B is equal to 2, 5, 3, part A, find B to the minus 1. Okay, Now you know how to do this. It's really, really easy. The determinant of b is the first thing you should always do. So that's going to be 6 minus 5, 1. And then you just, okay, if its determinant is always 1, then it's just 1 over 1. So it's 1 equals 1 over 1. And then you swap the leading diagonals, 3, 2, swap the signs of the others. Minus 1, minus 5. And you can get rid of the 1 over 1 for that. So that's the inverse. Question 2. And you can use this to solve equations now, because you've got to remember, let's just say, so find matrix, this is part 2, not separate. So find matrix A such that BAB equals the identity matrix, and we know what B is. B is that matrix up there. Okay. So we have a situation where we've got 2, 5, 1, 3 multiplied by matrix A multiplied by B again, and that equals the identity matrix 1, 0, 0, 1. Okay. Now we need to break this down so we get A on its own. So what we do to the left side, we must do to the right side. And to get rid of these horrible matrices, I just need to multiply by the inverse. I'm going to just go back in to algebra there to make it a little bit easier. If I times the left side by b to the minus 1, I have to do the right side, and I have to do it in the same order. The order must be kept with matrices. It's really important. So the b to the minus 1 has to go on the front of the equation, which I have done there. And if you do that, you are left with these. That just becomes the identity matrix, which is effectively 1 in matrix terms. So I'm now just left with AB equaling, and again, that just becomes b to the minus 1 because the identity matrix is just 1. It's looking a little bit easier. I now have to multiply by b to the minus 1 again, but I have to be careful. I have to do it on the right-hand side this time. Left-hand side, it doesn't matter because they're the same both sides, but I have to do it on the right-hand side to keep these b's together, which means that they can form the identity matrix. You've got to get it in the right order, so important, and they've got to be together in order to be eliminated. So on the left hand side I just get A, and on the right hand side I've now just got the inverse matrix of B times it by itself, and the inverse matrix of B I worked out earlier on, it was 3 minus 5 minus 1, 2, and I just need to multiply that by itself. A little bit of practice, so it's going to be 9 add 5, 14 I think there, and on the next one we got minus 15 minus 2 minus 25 3 minus 5 there, and then 5 or 1. That's often where I might have made a mistake there, but hopefully not. You can always check on your calculator. And that is how you work out the inverse, and the use of the inverse as well. We can eliminate matrices and find out new ones very easily. So I want you to have a go at exercise 6D now. Just do these questions 2, 3, 6, 7, and then 9 to 13 inclusive. Okay. That will take you a little while to do, I imagine. So do finish that one first before you watch the next video. Which is on 3x3 matrices, inverse of 3x3. But just, crack on with that one when you're done. Okay, well done guys, and see you in the next session at the 3x3 matrix.